Welcome to The Explainer. Today we're laying out a definitive, step-by-step engineering blueprint for safe, stress-free Solana deployments. Because, let's be real, if you've ever pushed an app to the Solana mainnet, you know the stakes are incredibly high. Your heart rate probably is too. Our goal today is to give you a structural, completely foolproof methodology to identify, test, and absolutely mitigate your deployment risks way before a single mainnet transaction ever takes place. Think of this as your master architectural schematic for deployment survival. Seriously, why wait for mainnet to break? Testing in production is just absolute terror. The literal worst time to discover your RPC endpoints or bottlenecking is when thousands of real users are mashing by with real funds, right? Sweating over your keyboard and just kind of deploying by hope, that's not an engineering strategy. By bringing these failures into a local, controlled, simulated environment, we can watch our systems break safely. We can patch them, retest them, and deploy with the cold, hard confidence of mathematical certainty. So here's the procedural blueprint we're going to follow today. First, moving from measurement to mitigation. Second, mapping signals to checklists. Third, simulating RPC rate limits. Fourth, simulating CPU saturation. And finally, building the debug report. All right, let's dive straight into phase one, from measurement to mitigation, where we prioritize our risks. We really need to shift our mindset here from simply observing our system to actively defending it. In any rigorous pre-deployment phase, your performance monitoring is going to flag concrete symptoms. Maybe you've seen those dreaded intermittent 429, too many requests responses. Or maybe a request latency suddenly spikes when synthetic load increases. Or perhaps there's a rising ratio of queuing time to actual processing time in your node metrics. Recognizing those symptoms is a great start, but our ultimate goal now is to actively prevent those strains from turning into incredibly expensive mainnet outages. So we prioritize these risks based on likelihood and impact and design targeted surgical mitigations to reduce that deployment surface area. Moving right along to phase two, mapping signals to checklists. This right here is the engine of our blueprint. We're translating abstract metrics into concrete engineering actions, mapping those scary system signals directly to their mechanical fixes. It's like a literal engineering spec sheet. For instance, if your monitoring shows HTTP 429s and a rising P95, meaning your slowest 5% of requests are really lagging, well, your RPC endpoint capacity is the issue. The mitigation? Implement rate limiting, request queuing, and auto-scaling. Now, if you're seeing high CPU percentages and long run queues, your container quota is the bottleneck, meaning you need strict resource limits or horizontal scaling. And finally, missing traces. Those point to observability gaps, which you solve by adding direct instrumentation. It's just a perfect one-to-one mapped schematic. With that schematic map in hand, let's calibrate our first simulation, simulating RPC rate limits safely on local. Now, before we execute, we have to gather our tools. And honestly, the beauty of this entire blueprint is that you absolutely do not need complex, expensive software to run these simulations. You just need Python 3.8 or higher, and a few really simple packages like requests for our HTTP calls, Prometheus client, and pseudo to monitor host performance. These packages will let us build local load generators that are completely isolated from the mainnet, so no real funds, no wallet signatures, just pure, safe, local stress testing. So how do we safely reproduce these RPC rate limit symptoms? Well, you'll start by firing up a local Solana test validator or pointing to a mocked RPC service. Then, you execute the rpcload.py script from your simulations directory. This script is going to actively hammer that endpoint with concurrent JSON RPC read requests, intentionally pushing the system until it finally breaks. Then you literally just sit back and collect the response codes and latencies to see exactly when and where those 429s pop up. This whole process brilliantly illustrates the exact transformation we're aiming for. Think about it. We start with a failing state, right? Intermittent 429 responses causing user transactions to just drop out of nowhere. But after applying our mitigation patterns, we achieve a tightly controlled system. Instead of crashing during a massive NFT mint or some huge token drop, your rate limiting and queuing configs step in to gracefully handle those crazy traffic spikes. Okay, let's switch gears to phase 4, simulating CPU saturation. We've conquered the network, so now let's look at artificially generating local compute stress. By running these next steps, we can mimic container resource saturation right on our own host machine.
You'll launch the CPU stress underscore monitor.py script, which deliberately spawns CPU-bound workers to just chew up processing cycles. As it aggressively stresses the host, the script samples CPU usage and watches those run queue metrics climb, writing all that glorious failure data straight to a local text file. Basically, you've just safely reproduced a catastrophic computational bottleneck, all on your own laptop. Now, notice how we translate the absolute chaos of a maxed out run queue into pure engineering stability. We take the measured symptom, which is a CPU maxing out at 100% with tasks backed up forever in the run queue, and we apply our mitigations. The mitigated result? The implementation of strict container resource limits and horizontal scaling. We are essentially putting governor limits on our engines, ensuring they never overheat and fail when the actual mainnet pressure is on. Finally, we arrive at Phase 5, building the debug report. Now that we've actively and intentionally broken our local systems, we have to meticulously document our findings. I really cannot stress this enough. The debug report isn't just paperwork, and it's definitely not bureaucratic overhead. It is your ultimate proof of concept. It's a technical document that proves, without a doubt, that your local fixes will hold up under mainnet pressure. It creates an unbroken chain of accountability from the simulated failure straight back to your checklist items, through a very clear root cause analysis, right to the validated mitigation. It's basically your architectural stamp of approval. You'll want to make sure your report includes some specific core deliverables to securely link your observed failure traces straight to your deployment checklists. First, clearly document the exact failures you reproduced, then follow that up with an honest root cause analysis of exactly why the system broke. From there, propose specific targeted mitigations, and this is the most crucial part, validate those mitigations against your monitoring outputs to actually prove the red lines went back to green. And this brings us to our final and arguably most important question of the day. Are your mainnet funds relying on hope, or are they relying on hard, simulated data? Because let's be honest, deployment by hope is a gamble you will eventually lose. But by using this explainer's blueprint, by shifting to active mitigation, mapping your signals, running safe local simulations, and building a rigorous debug report, you can deploy your Solana applications with absolute confidence. So take this blueprint, run your simulations, and fortify your system before the mainnet ever has a chance to test it for you. Thanks for joining me on this explainer, and happy deploying.